totally soaked. I wasn't teaching classes. I don't teach on Wednesdays. So that was fine. Also about me, Maxine was up for 2 hours in the middle of the night, so if my voice sounds a little groggy or my intuition is slightly underdone, that's the reason. Okay, so let's just remind ourselves what we did. The basic idea with maximum likelihood estimation is, I think, in a lot of ways pretty simple. Where I don't have my handy notes written up, but you can remember I just turned to look at them, even though that was like 3 days ago. What we're doing is sort of pre-building the data generating process. So we're going to make assumptions about how the data is generated, which is sort of a flip from how we thought about OLS. In some ways, OLS does make distributional assumptions, but it's an incredibly flexible framework where we don't have to make strong assumptions about where the data is coming from. What we're doing with maximum likelihood estimation is essentially flipping this. We're going to say, let's assume we know the general functional form of how the data is generated, but we don't know the actual parameters of that model. And what this does is give us sort of a more flexible framework. So the notation we developed last time, so we have our outcome variable, which is yi, just like in OLS. We have our observables. So these are the things, in addition to y, that we can measure, which we're going to use as predictors. And then we have the parameters of the model theta, which the way we think about this, theta is parameters that we're trying to estimate, but the true parameters of the model are never going to be observable to us. So we say they exist, but we're never going to be able to observe them. We're going to estimate them, but then we're going to try to make claims about where they are on the distribution, even though we don't observe them. Okay, so this is some of the notation. We have y. This is the function, and this can be very flexible. So we're going to talk about some different models. And then we're going to make a similar kind of assumption. So so here we have, with our classical linear regression, we have this conditional outcome. So we're trying to we're estimating y conditional on x. So this is the kind of claim, and then we can assume that it's normally distributed. So this is one of the assumptions, and then the mean is just the beta times x. Okay, so nice. And then we have the variance. This is one functional form. We spent the beginning of the class, or the beginning of this notebook last time, talking through what this looks like in practice, using just an analytical approach, which we're not always going to be able to rely on, but I think for developing some theory and some intuition for what's going on behind the scenes, doing the actual math is just incredibly useful. So this is this is the what is this? Psi? I can never remember the name. Phi. Yes, thank you. Phi. Faux fum. Yeah. So should we call this faux? And then this is the model that goes into the normal, right? So this is our standard normal. We're taking our x, so whatever the data is, we're multiplying it by our beta, which gives us the average prediction, and then we're subtracting off that, so the average prediction at xi, and then we're just subtracting off yi. So this gives us the difference between our model and our prediction, the data and our prediction, and then we're dividing it by the standard error, or the standard deviation, which normalizes this. So this will be centered on 0 and have a standard deviation of this, of f, that's 1. So all we're doing with maximum likelihood estimation is essentially we're just taking these likelihood functions, right, the distribution functions, and multiplying them together, and thinking about the densities given our parameter values. So the picture we had from last time looked something like this. So this was, this is just essentially I mean, I gave you some actual numbers here. They're not that incredibly important. All we're doing is just multiplying a bunch of these densities together to get our likelihood function. So this is just each of the densities multiplied together, which you can sort of think of as flattening out in some way, like the distribution. And we're thinking about the beta 0, which in our simple case is just the vertical intercept. So it's going to be the average. And all we're doing is thinking about the distribution of likelihoods. So where in sort of beta 0 space is most likely for the average to be. So we're drawing some data from an underlying distribution centered on some unobservable beta 0. Where is that beta 0 going to be given the data that we're observing? Up until this point, this is all just multiplying things together to get our likelihood function in ways that hopefully feel pretty familiar. This thing is, the maximal value, you can just see this on the picture, happens at beta 0 equals 1. And we can just, we can check that we can get this computationally to confirm just the visual. So this is, I'm just running optimize, minimize scalar. We're going to do this in a different way a little bit later, but this will work for now. And then this is our negative example likelihood. So this is, I had 3 observations, -1, 1, and 3. And then I defined the negative likelihood. And then we're just trying to find the optimal value on this bound. So then running this, I get a beta 0 equal to 1, which is exactly what you'd expect from the figure I set up earlier. So we're essentially taking a first derivative. We're doing it numerically, like we started introducing in topic 2, using small increments. Behind the scenes, this is doing that sort of gradient method, and then we found our beta 0. The height of the function is this, which in general is not going to be that meaningful, but just to give you a sense of what that number actually is. The area under the curve is going to be 1, so it's going to sum to 1, and it's going to give us this thing. All right, any questions there? Yeah, wait.
Why is the height of the function not meaningful?
So I guess when I say that, I mean, like, this is the maximum height, but what the height is telling us is the specific likelihood at any given point on the horizontal. But to say that 1 has a likelihood of this number, the main thing that's relevant about this number is just that it's higher than any other. But the actual value itself isn't, like, we don't usually use it, if that makes sense. Okay, any other questions? Great. So unfortunately, this thing is gross. If you're trying to maximize this analytically, like, you can do it. So 2 problems we talked about. One is that it's you can do it numerically, but the problem is that we end up with very small numbers. Each of these you can think of as being a very small number itself, just the height of the function. And each one of these, the distribution will sum to 1. So then we're multiplying a bunch of them together, which gives us numbers that most computers most of the time will treat as basically 0. So you end up with these rounding problems. The other thing is that taking derivatives of this function are gross. So you remember the trick we performed last time? We took a log. So a log of a product is a sum of the logs. So that looks like, so we could do this because it's a monotonic transformation. So that looks like this. So monotonic transformations, here we have this monotonic transformation G. We're just applying the function to the original function f, which changes its height. But like your intuition in utility space, like comparing utils is incredibly meaningless, right? All we care about are relative values. Like we want to find the highest one, doesn't matter what the actual value is. So that's what we're doing here. We're making one function produce different values while preserving the local optima. Okay, so nice. So what we do is we find the log likelihood. We take the log of the likelihood function, and then it ends up looking like this. And this is the thing we actually generally work with. So this is we use this little l to denote the log likelihood, and it looks like this. So it's just the sum of the logs of each of the probability distributions. So when we do this in practice in the code, it's going to look like, in this example, it's going to be a log normal distribution. So we can just take the log of the distribution itself, and that gives us something just directly to work with. So we're actually not even, in general, going to take logs. We're just going to use the logged distribution. Because the code lets us just skip that step. Any questions here? Okay. So let's just run this. So this is an example of this. So I have stats.norm, and then this is the log PDF. So this is the PDF, the probability density function for the normal distribution. But here we're doing this in logs. So we can just ask the computer to give us logs directly. And then for each one of my data points, I have 1. So this is my y. And then I'm just trying to predict the y using beta 0. It's our one parameter, and we're just trying to predict the y with that one parameter. And then I'm just doing that for each of the 3 observations. Because this is in logs, instead of multiplying, I can just add these things together. Which computationally is a little nicer, although not that much nicer. When I run this, it looks like this. So I have the log likelihood function here, and then this is the theoretical prediction. Okay. And that looks exactly as you'd expect, I think, I hope. If not, then good chance to ask questions. Okay, so so this is all really nice. So the idea is, earlier we ran the same approach using non-logs, and we just computed using a gradient method. We computed beta 0, not using logs. But now I'm running this with logs, and I get the same solution. So this is just confirming that the mathematical transformation of using logs gives us the same answer. Okay. So this is nice. So uh, uh, I wish these were maybe all on the same slide, but essentially this is the log likelihood. This is definitely different from the number that we got earlier. That was like 0.0001 something. This is a different number. This is the height of the log likelihood function. Here it's negative. That number is only meaningful because it allows us to use a gradient, right? Like we're just trying to find the highest value. It doesn't have to be positive. All we need to do is find the highest value. In this case, it's negative because we're taking a log of the thing. But what we can do is just take that value and plug it into an exponential. So we can exponentiate the logged value to get the original one. So I have both the exponentiated one and the one we computed directly. And you can see they are identical. So the only difference here, we found the same solution. The only difference is that the sort of the value of the function that we've maximized, or maximized in this case, the value of that maximized function is different, but it's only different by a log. And it turns out it doesn't matter. We don't particularly care about these values, although it's good practice to check them. Okay, so nice. This is actually one that we could have solved analytically, and I just want to walk you through some of the derivation. Well, I guess we did most of this last time. Remind me, we got through most of this exercise. No one remembers? My memory is that we got through most of this. Okay. So let me just remind you of the solution steps. We're going to do, I took out one of the examples. There was a multinomial example that I had in the slides from last time. I think for the sake of time, I don't want to get into it. If you want those notes, I can send them to you, but we're going to do, I think, 2 examples after this one. We'll do a Poisson, and then we'll do a uniform. I just want to show you some nuances, but we don't need to get too deep in the weeds. The key idea is I need you to understand the steps that are happening behind the scenes. Any good application of maximum likelihood, you should know what's happening. But in practice, we do this a lot with code. Like we're going to write down a function and then use a solver to find the maximum. And it's incredibly flexible. So here we're just going to take to find the maximum, we just find the first derivative. So we're thinking about the function and we're trying to maximize it. The log likelihood is this thing. So it's the sum of the logs. And then to maximize this, we take the sum of the first derivatives of each one of those logs. The derivative operator is linear. And it turns out to be this thing. So we have the negative of the first derivative of the normal function over the evaluated normal function, which is this thing, which it looks kind of gross, but turns out the derivative is kind of nice. We said the first derivative of this thing, with respect to z, is this. It turns out it's just the negative of pho. Thank you, times z. So it's the negative times of the thing multiplied by its input value, which makes sense from the exponent. So what we did is we took that idea back to our function, and we plugged in, using the chain rule, we plugged in this thing. So we said it's the derivative of pho is, this one's going in the books. This will be on repeat for forever. so it's the derivative of this times the derivative of the inside, right? Just by the chain rule. So it's this thing times, and then we're taking the derivative with respect to beta 0. So there's a negative here, which cancels with this. And then we're just left with this. So we could write it all out if we wish, but this is just, you can perform this on your own. This is just the chain rule. So the derivative of z with respect to beta 0, where z is yi minus beta 0. And I forgot a subscript 0 here. Any questions? So chain rule, all calculus, I think all of you are pretty familiar with. This is just optimization. And then what we do is we set this equal to 0, and then solve for betas. So in this case, all we're going to do is rearrange. So you have this sum over yi's minus beta 0, but you can separate this out into the sum of the yi's minus the sum of the beta 0s. Beta 0s don't depend on I, so that's just n beta 0s. So it's n beta 0 is equal to the sum of yi's, which then you can just rearrange to get this thing. So this is beta 0, our estimate, so we'll put a hat on it, is equal to the sum of n, or 1 over n times the sum of yi, which is just the average. Which I would say this is about as sensible as it gets. Any questions here? So this is nice. This is what we do if, so all of this is the first order condition if the only thing we're trying to maximize is our beta 0. But we can perform the same thing if we care about the standard deviation. So if we're trying to estimate the standard, like the spread of the normal, we can take a first derivative with respect to sigma as well, which looks like this. And I think this is about where we ended. Actually, I have memories of us doing the Poisson. Okay, yeah, so I think that's maybe where we ended. This is some weird latex here. I grew up on Legos. Okay, I'm never going to top the faux joke that's going to be the peak of today. Sometimes I substitute unrelated observations for jokes, and it never lands, even for me. Okay, so let's get back on track. This is the estimate we just talked about for beta hat. This is, I just worked this through. This is so it's the square root of 1 over n times the sum of the squared deviations from the truth. From the average. So this is just, this is very similar to how we calculate standard deviation directly. Just the difference is that with OLS, the variance is this thing, so it's 1 over n minus 1. So the n's are slightly different in maximum likelihood and in OLS. And what this means is the maximum likelihood sort of overestimates in some ways the variance or the standard deviation because we're sort of off by 1. Okay, this means it's biased downward, like we're being sort of overconfident in our estimates because the spread of the maximum likelihood is has the 1 over n instead of the 1 over n minus 1, then the spread of the estimate is going to be a little bit tighter than in OLS. Okay, so nice. So this is all review. So then, numerically and analytically, we can get the same solutions. You can just plug these numbers in. The sample mean is this. The sample standard deviation is this. And we said from the analytical solution that the best guess using maximum likelihood estimation after we worked through that normal example should be the sample mean. And then we calculated it. And oh, I'm sorry. This is a different data set. Here we're actually collecting a larger sample of 1,000. So the sample mean is 3. The sample standard deviation is 2. And then all we're going to do is actually run an estimation over this. So we're just going to use SciPy optimize, and then we're going to use this, which is our maximum likelihood estimator for the log likelihood. So we're looking at normal log PDF, plugging in the y value, centering it on theta 0, or just theta, but the first one, and then we're using the scale, which is just the second in our theta parameters. So if I run this, and then we actually perform an optimization. I'm going to run this, and then we'll talk about the details. The MLE, it estimates this, which is identical to what we'd found before. So the theoretical solution, we walked through the analytical solution, and then used the analytical solution, and then just plugged in our numbers. The analytical estimator for theta, for our beta 0, was just the average. And then the standard deviation was identical to this number. So this is just to confirm that running an optimizer in this way gives us the same answers that the theory predicts. Let me show you a few things here. The first thing is that my method is not directly the standard Newton-Raphson. The first thing is, so BFGS is just sort of a fancy version of Newton-Raphson. L just means we're doing this in logs. I ran this without L, and it didn't converge. So sometimes you just want to be careful with which optimizer method you're using. And then this B is just for bounded. So this lets us do a bounded version. So we don't have to check everywhere. We can just check on some interval. So when we use this B, we can then add the bounds. And I'm just saying I don't actually care about the bounds of beta, but I do care that in the search space, I don't want to look for negative standard deviations. It doesn't make sense, so I'm just going to make sure it's above 0. Okay, any questions here? Yeah, Eiley.
Why didn't you just make the bound 0 instead of 0.01?
Let's see what happens if we do that. So yeah, nothing changes.
Cool.
Any other questions?
So did you just choose 0.01 before because it was like really close?
Yeah, just very small. I expect it to not be anywhere near 0. But yeah, it seems 0 works just fine. Okay. So that's nice. I think last time we talked about just visualizing the concentrated likelihood slices. So this is just, I have, they're sold at, concentrated likelihood functions are sold at Trader Joe's. They come in the little boxes. They're really delicious. These are just, we're basically just holding one of the two estimates constant and then checking different values of one of the estimates. So this is it's almost like a partial derivative with respect to one, and then we're just going to visualize the different values, which looks like this. So you can sort of see the picture, the 3-dimensional picture, if we plotted this, would be convex up, right? It'd be like there's a nice surface with a maximum, and we're just trying to find the peak in 2 dimensions. Any questions here? Okay, so this was the Poisson example I think we ended with last time. This is the Poisson probability density function, or probability mass function, because this is discrete. Poisson is just really good for like counting things. We can control like the spread of the thing using lambda. And lambda happens to be the mean. So we're going to go through and estimate lambda using some actual real world data in a second, but we're going to work through like the analytical solution. This class, we have both, lots of computation, but also behind the scenes, often we can do more powerful things with computers if we do the math first. That's a general principle. Like, you can do lots of things by brute force, but you can make things go much, much faster and sort of ground what you're doing in correct theory. Like, you can prove that what you're doing is good using the math. And then we can just implement the math with code. I think when I was younger, I thought, like, why don't we just run everything brute force on a computer? And it turns out that can work for a lot of things. That's like what a Monte Carlo kind of does. But I think I've shown you that Monte Carlo isn't necessarily the best approach every time. Like, if we care about precision, we should be thinking analytically as well. So sort of taking a computer with good mathematical theory hand in hand is the approach. Okay, so this is the probability mass function. I might call it probability density function, but it's just the probability function. Good for counting. So what we did is we said we're going to draw n IID draws from some underlying probability function of Poisson. And all we're going to do, just like before, is just look at the log likelihood function. So this is just the sum of the logs of the probability functions. These are independent, which is important because they're not impacting each other. You could model this. You could model non-independent data, and I expect you could probably think about how to do this. You need some way of relating the draws one to the one before it. But you could do this with a sum. It just looks gross. So that's independence just tells us that each one of these things looks identical. And then identically distributed tells us about identicalness in a different way, which is that the parameters are the same. So the lambda is showing up exactly the same for each one of the draws. So what this does is gives us a nice sum. I think that second one is actually probably the more important one, because we need the underlying like parameter value to be consistent across draws. So this is just the sum. If you take the log of this ratio, it gives us this. The exponential goes away, just leaving us with lambda, and then we have the exponent comes outside the log, and then we're just taking the log of lambda. This last bit turns out to be pretty unimportant. When we take a first derivative, it actually goes away. So this derivative just looks like this. And then this is the first order conditions. Set it equal to 0, solve for lambda, gives us lambda hat, which just the average. Any questions here? Okay, so this is another example. This is uniform. And this turns out to be a little trickier. Let's just walk through some of the details. I include this. I almost took this out, but I wanted to include it just to communicate that we have to be careful about how we're thinking about the likelihood function. Which is like, I think like every topic is like, be careful. So we're gonna have a series of uniform draws between 0 and theta. This is a simple case. We could have, two parameters where it's not between 0. It's like theta lower and theta upper. This is a simple example just to illustrate the problem. This problem would show up even if we had control of the upper and lower bounds. We're just making a bunch of draws, each one u, and we're just going to assign 1 over theta if it's on the interval, and then it's 0 otherwise. So this is just the standard function for the uniform distribution. This is very simple. When we construct the likelihood function, it's just the product of each of the probabilities. Because it's uniform, the probability is just 1 over theta. So when we multiply these together, we get 1 over theta to the n, whatever the sample size is. Okay, and then we need theta to be less than the maximum greater than the maximum of the observations. So we don't know what theta is, but we know it must be greater than any of the observations we see. Like, we can't be drawing from above the maximum. So that's where this comes from. And this is the key step, that when we're estimating theta, the main thing we know is that it can't be, that it must be greater than the maximum of all of the things we've seen. Okay. So then the best guess we have is that theta hat is the maximum. You can't actually take a derivative of this and set it equal to 0. There is no maximizer in the same way. So the best guess we have is something that there isn't calculus to get us this solution because of this setup, right? This maximum makes that impossible. So there's not a whole lot extra to say here. It's just, the setup with this kind of problem is a little trickier than with the really nice functions that are defined everywhere. And we can just take a first derivative and set it equal to 0. This one's trickier. Okay, any questions? All right, you want to do an example? Do y'all like soccer? I watch soccer basically once every 4 years. This is a great example of maximum likelihood that's been bouncing around. We have this in the MQE for a while. And I think it's a great way of exploring a more complicated model. The basic setup here, we talked about Poisson, which are good at measuring counts. We're going to measure goals. So this is a great application of Poisson, just trying to count a bunch of things. In this case, we're going to have 20 teams. And what we need to set up any good model of gameplay is we need an attack score. So some teams are very good on offense. And then we need a defense score. So we need to measure how good the team is on defense. Good teams are good in both of these ways, and bad teams are bad in both of these ways in general. So I'm going to show you, first off, we're going to make naive guesses. It's going to be our, we need to initialize our optimizer. So we're going to have to make some guesses. I'm going to show you the naive way of thinking about how to estimate attack and defense scores. But then we're going to try to optimize this thing. We're also going to think about home and away. So I think you worked on a data set almost identical to this in the checkpoint. And you were thinking about Poisson and scores and all of this. So I think a lot of this will feel kind of familiar in that way. We're also going to try to estimate a home advantage score. And then we're going to think about identification. So can we actually estimate this thing? Okay, so here's the setup for the data. The English Premier League, I don't know that much about it, but it has good data, and it's something we can use maximum likelihood for. So we're gonna have 20 teams. We're gonna use 2 years of data. Some teams leave the league, and some teams are added to the league. So we're gonna use our second year and all of the teams in that second year, but we're also gonna include some of the data from the first year. So we're gonna have just about 380 matches, and we're just gonna collect it from this place. And then here are some of the variables. So we have the home team and the away team. So we have 2 teams playing each other. We have so the total goals scored by the home team. So this is full time. So this is in the full game home game score home goals, and then this is away goals. So AG is for away goals. So nice. So if we play at home, Arsenal plays Liverpool. We win Arsenal wins 2-1. We'd see the home team is Arsenal, the away team is Liverpool. Home goals would be 2, and away goals would be 1. So this is just how the data is going to look, and then we're going to use this to estimate how good each team is on offense and on defense, and their home advantage. And you can think about the trickiness of this problem, right? Like each team is going to play a bunch of other teams, and depending on the quality of the opponents, like if you play a very strong defense, you're not going to score very much, even if you have a strong offense. So we can't just go in and say, like, let's look at which team scores the most. That's going to be naive. Like, it's going to miss the fact that some teams have good defenses, and that will contribute to the scoring of that team. So this is a tricky problem because we sort of have this like matrix of relationships between offenses and defenses depending on like who's played whom. Okay, so this is going to be the model we take in. So you'll remember with maximum likelihood, we have to specify the underlying distribution of the data. So we're going to say, because it's a count, we're going to say that it's Poisson. So goals scored by the home team, we're going to define this as being drawn from a Poisson distribution with lambda. And we have 2 subscripts. One is for the home team, which will be I, and the away team will be J. And then this is the lambda for the home team. So we're just specifying the pairings and then whether this is home and away. And then we also do the same thing for the away team. So this is team I is playing team J, and we're looking at the parameter for the away team. Any questions here? So let's just define this. So we're really, the main, the first question is how we set up the parameter lambda. We wanted to capture attack quality. So if you're very good on attack compared to another team, on attack who's less good. If you play the same team, you should score more on average. But it matters who you're playing. So we have to hold all of these things constant. We have defense qualities. So again, we need to, so if your defense is good, you play a good offense, and you play a bad offense, there are going to be different scores for the opponent. So that's one way we can sort of like if you're thinking about the number of parameters we can use in our model, you can think about how we would sort of make just direct comparisons if we can control everything. We're going to talk about identification. This is a key part of how we build these models. Like what structure can the data actually support? And then we also have information about whether you're playing at home. I'm like a semi-casual sports viewer. Home advantage is a weird thing. This is how we're going to set up the parameterization. And let me show it to you, and then we'll talk through each of the details. When I take the log, so this is the model. This is the functional form we're going to use. And we're going to talk about link functions quite a bit in the next week or so. This is what we'll call a link function. I'm going to define it more formally, I think near the end of class. But let's just look at the function itself. So this is the parameter, right? So this is the lambda is the thing that we're drawing data from. So we want the parameter, which is going to impact the score for the home team. We want that to be a function of relevant factors. The first thing is just going to be like, if in hockey, well, I don't know hockey that well, but in basketball, the high, like the scoring happens a lot, right? Like, and the final score is going to be very high. Just in general, it's like, I don't know, in the NBA, it's like 90 to 100. So the baseline score, am I right? Anyone watch the NBA? Okay, sound about right? Usually over 100, okay. So this is going to control the baseline score. So this is like something about the baseline scoring. And then to that, we're going to add a home team advantage. So if your home team advantage is high, you'll score a lot. And if the value is smaller, maybe you have a home disadvantage. Alpha I will be the attack rate or the attack strength. So this is just how strong you are on offense. And then we're going to do this with negatives. So it's going to be negative delta. It will be the defense strength. But this is the defense of the opponent. So my score as a home team will depend on the negative of the strength of my opponent. So this is just a baseline score rate. So if we like made the goal in soccer 4 times as big, mu would go up. Just it's much easier to score. Nu it controls how important the home advantage is. This is the attack for the home team, for the team we're considering, and then this is the defense rate, which is negative. We want it to be we want strength on the defense to negatively impact the team. So this is all for the home team. For the away team, all we're doing is we're taking out the home team advantage. So we're gonna just not have that in the away team. You could set this up as like a negative, eta in the second one. That would change the interpretation of eta, or nu, I should say. Is this eta or nu? Um, who knew? Okay, I tried. So this is exactly the same, just with the subscripts flipped, and with the home advantage taken out. Eta, thank you. So eta doesn't show up in the second one, it shows up in the first one, and all we're doing is, for the away team, we're just not including a home field advantage. Okay, I want to just talk about this last line on this slide for a second. This looks like a lot, and I just want to specify like what this whole thing is doing for us. There's some details here that do matter. This ensures, like, for the Poisson, we need lambda to be positive. So by specifying the link function like this, this ensures that lambda is positive. And think about why. What we're doing is we're saying this is the log lambda is equal to this linear combination of these different parameter values. If we were to take both sides to the exponential, so raise both sides to e, this gives us lambda on one side, and then it gives us e to the sum of these parameters, which we can then write out as the product of e to each one of these parameters. So no matter what the parameters are, if they're 0, e to the 0 is 1. If it's negative, e to that negative is a number below 1. And if it's e to the some large number, then that's a large number as well. So this just ensures that lambda is going to be greater than 0. And it also makes it multiplicative. So if alpha is 0.3, then we're saying the team scores roughly 1.35 times as many goals as the baseline. So this is the idea for why we're setting it up this way. It's the log of the lambda is linear, which means it's multiplicative in the exponents. Okay, any questions here? We're deep in the weeds. I want to just step back for a second to think about what we're doing. We have complex models. Like, this would be very, like, you could do this with a general linear model, with like OLS. You could set up this relationship between the parameters and go in and try to estimate it. But you're going to misspecify. This is, like, scoring is not linear. It's going to be more complicated than that. We're trying to count things. Poisson is the natural way of doing this. So what do we need to do? We need to be more specific about the data generating process. We think it's accounting, so let's set it up with counting. From there, we need to know what the different parameter values are for the Poisson. So then we go in and we specify this model. Then using our maximum likelihood techniques, we can specify a log likelihood function using this model, and then minimize it using our computational methods or numerical methods. That's the high level. Like, some things are, like, the core reason we're doing this is because some things are not great with OLS, and this is a great application of that. All right. So I just want to spend one slide talking about the identification problem. Think about the amount of things, like the number of parameters we could include in our model. Like, I don't think in grad school, I don't think I like fully grasped a lot of these ideas. The number of parameters is related to, like, the structure of how the data is generated. We have teams playing each other, so that gives us some idea about the relative strength of the offense and defense. If two teams have 0 defense, you're just gonna, like, the score is going to be 100 to 100 in soccer. So the height, like the amount of goals tells us something about the defense and the offense. And the relative strength of one team playing 2 different other teams tells us something about the strength of the defense and the offense. So if you hold offense constant and then change the strength of the defense against 2 different opponents, you can get some information to estimate the parameters. So just thinking about like the sort of the pairwise structure of how games are played, and then that you can play at home or away for this against the same team. This gives us sort of the amount of parameters we can set up. So you couldn't just like include as many parameters as you want. That's the identification challenge. Here, we have 20 attack parameters, 20 defense parameters, and then we have these 2 global parameters. One is controlling like the base score, and then one is controlling the home advantage, just globally. We have 42 parameters in general, overall. And just I don't want to dwell too deeply on this, but the way the data generating process happens, we don't have enough parameters, or we don't have enough sort of structure to our data to be able to estimate 42 parameters. I'm just thinking about the way the teams play each other. We just don't have enough structure in our data to estimate 42 parameters. So the core idea is that we don't necessarily need to estimate all of these parameters. This is an important thing to, like when you're building your models, you need to be thinking about whether you can actually identify it. And it's, the key thing here is that we can actually normalize. I don't want to talk too much about the math here. It's not so important. But what we can do is just normalize sort of our global parameters in our offensive and defensive parameters in this way. So think of this as sort of like turning some of the attack and defense into a standard measure. So we're just saying, on average, the attack parameters will be 0, or in some will be 0. Some will be greater than 0, some will be less than 0. This just allows us to set a baseline for attack. We could set attack however we want it if we didn't do this. We could say everyone's attack is very, very good, and everyone's defense is very, very good. That's why we end up with close games. So that would be one way of parameterizing this model, but then another way of parameterizing it is that both attack and defense are not very good. And both of those assumptions could fit the data equally well. So what we're doing is we're just saying, let's not worry about that. The levels are not going to matter. We're just going to say all of the attack parameters and all of the defense parameters should equal 0, should sum to 0. So this is a normalization, and I think seeing this in the data is one of the more challenging parts of doing empirical work and building statistical models, like recognizing that you're not going to have enough parameters, or your data can't support this 42 parameters. This is one of those problems that you'll learn with practice. Okay, so what this means is once we've done this normalization, if alpha is greater than 0, then you're above average. So that's how we're now interpreting alpha, where before it could float. So an alpha greater than 0 would not necessarily mean that you were above average. And now also we do the same with defense. So if delta is greater than 0, then you're above average in defense. So what this means is we have one additional equation for attack and one additional equation for defense, which takes us down from 42 free parameters down to 40. And that's just enough for us to be able to estimate this. Any questions here? Like my econometrics professor is like, any questions? Any questions? And then move on that fast. Great guy. Loved that class. Okay, so let's actually do this. Do you want to take a break now or after we do this? Let's do it. We've set up the model. Let's do it. So I have 2 seasons, and the reason we're using 2 seasons is just to get more observations. We could do it with 1 if we wish, but 2 is better. So I'm just going to directly load the data set from footballdata.co.uk. And then we're going to print out a couple of things. So the first is going to be the number of matches per season. And then I'm just going to list out the columns for the data set. So here we have div, date, time, and then our score measures. So home team and away team. So this gives us information about who's playing who and what the score is. And this is going to be enough for our purposes. So this is just a list of all the teams in the second season, so the 24 to 25 season. And what we want to do is only include teams that are in the second season. So what I'm going to do is for the first season, so the 23 to 24 season, I'm just going to take the data set, the teams where both the home team and the away team are in the second year. So for the first year, because some teams enter and some teams leave, I'm just going to toss out any games that are played between teams that aren't in our main data set. The reason we're doing this is just to give us more observations for estimation purposes. And then I'm going to call this seasons joined. When you're writing variables, it's nice to just call them things in English instead of like abbreviations. I'll show you some bad examples. I mean, this is borderline for me. Param table, just say parameter table. So we have the number. So this is I'm just indexing teams, giving them a number. I'm defining a sort of just initializing this as 0 for the alpha and then delta. So this is the parameter table as we start. But then we also need to set the global parameters, which we'll do in a second. And then all I want to do is sort of restructure the data to give us data that we can use to estimate. So nothing really interesting here. I'm just setting up a data set. So I have the home team, I have the away team, I have the full-time home goals. So this is the goals for the home team. And then we have the away goals. So how many goals the away team scored. We have the date, which we're not going to use. And then we have numbers for the home team and the away team. So I'm just setting up numbers for the indexes. Okay, so the last thing we need to do is set up the global parameters. So we have, using that table we set up, we have the parameters for the teams. And then we also need our global parameters. So we need mu and we need eta. So we're just going to set up a list of things. This vector called theta, which is just essentially going to be a list of of numbers. So I'm going to start with zeros. So we have 20 teams. We're going to have 40 parameters in total. So one attack, one defense for all. And we're going to have the global parameters mu and eta. Because we're normalizing, we're not going to include theta. Sorry, we're not going to include attack and defense parameters for all 20. The last two parameters are going to be so 38 is going to be for mu. So this will be the average away goals. And then this is just an estimate to get us started. So we're just going to say for the average scoring, it's just going to be the average scoring of the away teams. That's going to give us our baseline score. For eta, we're just going to say this is the home boost. So this is like the average initialization of our home field advantage. We're just going to say this is the difference between the home goals and the away goals. So we're just going to compare, on average, her middle name is Ada. Side note. Not spelled like the Greek letter. Although that would be cool. Maybe I'll name my next child Gamma.
The first one should be alpha, second one should be beta.
Yeah, exactly.
Didn't Elon Musk do that though? So.
Yeah, let's not do that.
Yeah.
So yeah, we're essentially just setting up the home boost using the difference between away and home, which is not going to be correct, but it's going to be ballpark. Speaking of sports. And then we're just going to initialize this. So this is nice. These are just our baseline guesses. We're going to call this theta 0. We started it with zeros, then we filled in each one of the values. And then we we'll go from there. So nice. So these are just some summary statistics here. Home team score on average 1.65 and away team score on average 1.4. And you can see here, this is very naive. We're not taking into account whether good teams are playing good teams or good teams are playing bad teams, which will impact the estimate values. This is just a place to start. It puts us in the region of where we want to be. In this case, it probably doesn't matter. You could probably start at zeros, but this is in general a good practice. So what I'm going to do here is just go through and be a little bit more specific about the initialized values. Here we have the average for home and away, but most of these we're not actually estimating. So if you print out theta 0, this is mostly going to be filled with zeros. And what we want to do is actually just fill these in. So what I'm doing here, this is, maybe it's not worth walking through this, but this is essentially just going through, we have our baseline, so this is sort of the average team performance. And then, so this is just, this is the mu, and then we're sort of dividing the eta by 2. So I'm saying, I'm just going to, on average, the baseline is going to be the average of home teams and away teams, which is the way these thetas are constructed. It's just like, we're going to take the away average, and then we're going to add to that half of the home advantage. So this is just the baseline scoring. And then we can walk through all of this, but basically all this is doing is just using the, the, the home team score and the away team score to give you sort of an average score for each home team. Sorry, the difference between the home team score and the baseline. So if you're above baseline, your alpha is going to be positive. So we're just going to use that idea to set to initialize the score for team I. So we're just going to run through all of this, run it through every team in the data set, and that's going to give us some initialized set of values, which is going to look like this. And if you want to print out theta 0, you can see what this looks like. So theta 0, when I do anything with code, I like to see exactly what the main objects look like. In this case, theta 0 is just literally a list of numbers. And we're just trying to keep track of which ones correspond with which estimate. Okay, any questions here? Now for, like, this is, I think what we just did is the hard part. What we're about to do is just implement it using maximum likelihood in with the theory we developed. So all I want to do to sort of keep things organized, the log likelihood is just the home team goals plus the away team goals. So we're thinking about the log likelihood of the match counts. So this is the log likelihood. We're just adding the two log likelihoods of the two teams playing each other together. These are the observed goals. So these are the things we observe, the Ks. So the actual score is the thing we observe, which is K. For the home team, we observe it for the away team. And then what we're trying to do is pick our lambda parameters. But you'll remember, lambda is the log linear in the parameters we're actually trying to estimate. So mu, eta, delta, and gamma. Oh, sorry, alpha. Greek soup. So all we're going to do here is just, this is just we're defining a few things at the top. The important part is setting up the negative of the log likelihood. So this is L for the log likelihood. I have some definitions here for what this function is doing, but essentially all we're doing is so we're extracting the values from the thetas, for the alphas and deltas, but we're taking in some theta guess, and then we're defining the essentially the objective function. So this is the function here. So this is just the sum of the log likelihoods, and then we're just doing this for each of the values. So I don't want to spend a ton of time talking through all the details here. If you want to get into this more, I have it written out, and I think you could spend a few minutes just thinking through what this is doing. But essentially, this is just implementing the log likelihood function. Once we have that function, it tells us the height of our log likelihood at any theta values. It's taking in the data sets. So we're actually defining the goals, so home goals and away goals, and then essentially telling us how close we are. So if I run this, and then we use our initialized guess, just taking the averages without really doing anything sophisticated, we get a log likelihood of this. It's very negative because the height is going to be very close to 0, and logs of numbers that are close to 0 are very negative. Okay, any questions about this? We can go into more detail if you want, if you have questions. Okay, so let's, so you can see that the data enters through this thing. So it's home goals, log factorial for home, and then that enters here. So this is like, this is the core of it. Simply writing down the log likelihood of the Poisson using the data and our guesses for the parameters. So we've just implemented our math that we've become familiar with in Python, which is the best language. I know you all agree. Okay, so all we're gonna do so here's the outline, right? We have the data, we build the model, we don't know what the parameters are, but we have our function defined. Now we have, from the beginning of the semester, or the beginning of this half semester, we have our ability to perform optimization using discrete methods, or numerical methods. So we're just gonna take that method and apply it to our -L for soccer. So our log likelihood function, and then we're going to give it an initial guess. This is the log version of the Newton-Raphson, but also allowing us to have bounds. I'm not actually defining bounds here, but I am giving some options. So set the max iterations. We don't want this to run forever. And then just some tolerance parameters. And actually, when I set these, I don't remember exactly what they do. But they're tolerance parameters. You could look up what ftol and gtol mean. And then this is just going to give us a result. So I'm going to run this. It took about a split second to run 26 iterations. And we can see we're printing out the convergence to be true. The log likelihood at the maximum likelihood is negative just about 2,000. And you can see the log likelihood from our naive initial guess was just over negative 2,000, just less than negative 2,000, larger than 2,000 in absolute values. So definitely our naive guess was like in the ballpark, but it was not correct. When we're dealing with these values, small differences can actually matter a lot. Okay, so why don't should we print out, let's actually print out the difference. Oh yeah, we do that down here. So should we take a little break here? I don't want to run too long on this. I think this might actually be a good spot to stop for a second. We've set everything up, we've run it, and I think now is a good time. When we come back, we'll talk about the results. But these are the results. I think like all the building blocks are in place for actually doing this stuff. And then we'll talk about the results, and then we'll talk about inference right after. What are we at? 11 minutes? So 10:36.
he was one of his professors, and I was like, what are you talking
My
about?
mom was like friends with like Cory Booker.
That's insane.
She knew him in law school and she's like,
You know the previous Supreme Court justice living like right next to DC is happens like more than anything, but Antonin Scalia would play tennis like right next to them, like we would be on like the court side by side, and he most definitely didn't like me. I was really annoying.
oh well.
Yeah.
He's annoying.
Yeah.
Yeah, I guess she was like the legal head of like the ECON.
That's so cool. How did it go well then?
I think so, but
Okay.
I mean they don't. The decisions go to
Mm-hmm.
Trump was like attending originally.
God. It's just like, I'm scared to like go back to DC and like reimbursement, like
scared to look at the news.
re-enter into that realm. It's the last thing I want to do. Yeah. How'd it go?
Did you have your shit?
Yeah.
I liked her. She was very like.
I know.
She like talked a lot, which I appreciate. Because I also have to go like that.
Yes. She did the same thing. I was looking like, I don't really know if I want to do remote.
Yeah, I like. Because she asked you that too.
Mm-hmm.
Honestly, obviously I was like.
Yeah, no, of course I was like, I love remote.
Yeah.
I know. I know. She was saying that like it was a positive thing.
I know.
It's the craziest thing I've ever heard.
Did she put their hiring for people? But
Oh, I didn't
think that was
ask.
all, like, I didn't ask either, but she was like talking, she was like, we're like hiring people and like you got hired 3 over, but I didn't know if that meant like 3 entry level or like.
Oh. Yeah, I don't know.
But
I have a follow-up interview next week with her, but I'm like, I don't know.
Yeah.
I also like asked her because they're all like sustainability and renewable energy and stuff, and so I was like, what is the status with AI usage with your financial analyst? Because like,
yeah.
that's whatever. And she was like saying how she uses AI and she thinks their researchers use AI. She was like, but I really don't think our programmers use it at all. Like I don't really see what need there would be in coding to use AI. And I was like, Queen, what?
The
What
question
are
will
you
be
talking
to do
about?
everything in Excel and the most is just
I was like,
so I'm
girl.
like, so we're not doing any actual
Yeah.
She was like, if you have any sort of building models or is that already templates?
She asked me that same question. I was
But
like,
what
what?
is the same message?
Yeah.
I don't know. I mean, we're working on Japan, Massachusetts, so like, what would be good?
Yeah,
Maybe
especially because they
finish all
pay
these-
for you to
yeah.
stay in Pittsburgh for those meetings.
Yeah,
back to New Hampshire so that every time they have a meeting, I get a hotel night.
Yeah. Because she asked me, she was like, where are you planning to live after graduation?
She asked me that too.
I was like, I didn't want that long here, but it would probably continue not East Coast,
Yeah.
but what's your second?
She asked me for times and I just sent them this morning, so either Tuesday or Wednesday is what I sent her.
Really? Yeah. She asked me the same thing. I did it Monday or Tuesday, so it's
Yeah. I also went to like a career fair through the city for the other day, and there was this one lady who was actually roasting me. Wow. I was like, this is, why am I getting like nagged right now? Well, first of all, I came up and I like went to shake her hand and I introduced myself and I was naturally like smiling on her. She goes, you seem very happy. Like that with that look on her face, and I was like, I just was like, okay, I'm gonna roll with the punches. And so I was like, yeah, like of course, like I'm happy to hear about like what your company's all about, like I'm excited to talk about the future, whatever. And then we keep talking, and I handed her my resume, which is the stable template thing in Times New Roman, and she goes, wow, I haven't seen this font in ages. And I was like, why are you like roasting my resume right now? I was like, queen. Like,
not a comic style.
I know, yeah, comics. I was like, alright, I'm gonna walk away.
Yeah. That's crazy. I feel like a lot of the resumes I see look like the exact template that's
Mm-hmm. And then I had like a bunch of printed copies of my resume from the fair, and I was about to drive home, and then I was already downtown though, and I remembered that Garrett said that thing about CGI, saying they wanted someone to walk in with their resume, so I was like routed to CGI, and I went to CGI, and I go up, and they had like, we need like a key card to get into their office space, but it was a clear door, all their lights were on, but everybody was away from their desks, like nobody was in there, so I think they were in a meeting or something. So I rang the doorbell first and no one came, and so I folded it up and I stuck it in the door and I left.
That's so funny.
I really threw it right in the trash. Yeah, I was like, why has no one reached out yet from my resume is stuck in their door?
Probably like throw it away.
Genuinely, you probably didn't even unfold it. I wonder what happened to that self-driving truck company.
Have you read it?
Yeah, she sent it to her recruiter, but then I haven't heard anything. And then I was messaging this girl on LinkedIn that works there that graduated from Kit, and then she goes to me. She was the one that was like, let's set up a call, like whatever. And I was like, great, let's do it. And she's like, when's your availability? And I sent it, and then she never answered. I was like, great, perfect. Amazing. To be fair, like the positions that I applied to, I'm not qualified for. It's like starting salary $200,000 a year. I know that is like. Oh, me? I thought you were saying she asked you that. No, I've done nothing in Excel.
I mean, like, I've like done some like data manipulation in
Yeah.
Excel. I was like,
I literally am like, I don't even. Yeah.
like I can like do it when you're doing
No, I agree. I don't really want to do something, it's just Excel.
Me neither. But they were like, she was like, I don't know
So,
I was like, oh, can you explain that bit? And she was like, well, I don't really know. That's more analyst.
I was like, okay, she was asking like all of these details about my capstone project, and I was like, wait, like, do you know anything about financial analysis or not? Like, I was like, I don't want to be rude by like turning it down, but also whenever I said anything, she was just like, oh, that makes sense, and I was like, I don't think.
I thought she was really nice, but
She was really nice, but I don't really want to. Yeah. I have my call with the crane people today.
Wow.
Get excited.
The one that I also applied, I would just imagine
Yeah, I would think it. I didn't know they only had 20 people.
honestly, for like
what was
The
the?
scale they have a picture is between 7 and 9.
Oh,
Which like for fully remote, I feel like they kind of pay less.
yeah.
And so like, if you could get somewhere like that, also like, it says on my graphic on my classes you was for 30 so I feel like
Yeah.
Say again?
I wonder how much this crane
Sorry to interrupt. Jobs are super important. How's it going?
It's okay. I'm just sick of talking to people.
Fair.
like pretending you're like so interested.
I know, the amount of people I've like harassed on LinkedIn
Yeah.
being like, so, I'm just ready to be done with it.
Yeah. We have PhD students who are also going through the job process, and I remember when I did it. I mean, mine was nowhere it's very different, but yeah, it's universally a very challenging thing. So I was going to show you this amazing little video of my child, but the speakers aren't working. So we'll save that for another time. You can come by my office and watch. This is the video I watch when I'm having a bad day and I just want to smile. It's her just giggling for literally 5 minutes, just belly laughter. Okay. Should we finish this up? Okay. 4 yeses, the rest abstained. I think that's 0 to 4. This is not quite a democracy, but we'll pretend it is for right now. Meaning the classroom. So this is the basic the output from the run. So what we want to do is put ourselves in a world where we can actually make interpretations. So we want expected goals. So this is the average goals scored per game. So this is eta hat plus alpha I hat. So our estimated mu and alpha, and then the average goals conceded per game. So this one. So this is we'll just run some of these things. This is just extracting our alphas and deltas. And then here at the end, we're extracting our mu and etas. And then we'll actually just print these things. So we'll put it in a data frame, run this. I'm not going to, I think Colab will give you an error if you actually try to save it. So I'm going to comment that stuff out. I saved it to my local computer, which is what that's for. So this is just our estimates. These are the different alphas and deltas for each team, and then we have the expected goals and then the expected goals conceded. And so what we can see here is this is sort of a measure of how productive each offense and defense are. And we're using mu, our estimated mu, because that's our baseline. We did this normalization technique to center our alphas and betas, alphas and deltas on 0. But that means mu is doing a lot of the work, just setting the level. So that's what mu is doing. So mu plus alpha. Okay, so this is nice. This gives us some nice estimates of the different teams. And what this is doing is taking into account the strength of the opponent when we estimate these parameters, right? We're not just simply estimating wins and losses based on just sort of independent of who the teams are playing. right? Often you'll see like average score, average goals per season, or some metric of success for a team, but that is a naive estimate. This is much more sophisticated and much more correct for thinking about the quality of the teams, because we have to match it with the opponents. All right, so this is nice, but we can also, I think the better way of seeing this is with a figure. So this is just a figure showing, so we're plotting, let's see. We're plotting on the horizontal axis, it's sort of the quality of the defense, and then the vertical axis is the quality of the offense. So if you're a good team, you're like up here. And if you're a bad team, you're in the lower part here. So these are the worst teams, and then because they have defenses that allow a lot of scores, and they don't have offenses that score much. And then these are the teams that score a lot and defend well. So this is just, a nice little picture. It gives us an indication of like the relative quality of different teams. Any questions here? I think in general, when you run these, if you can turn your estimates into something that's easily communicable, that tends to be nice. All right, so that's the basics, and so these are just some observations. I don't want to dwell on this too much, but it just allows us, with these nice conversions using the exponent, it allows us to make some nice things. But what I want to do, the last thing in this notebook, before we talk about inference, which we are going to absolutely cruise through, I want to talk about the generalized linear model, which is essentially a way of systematizing maximum likelihood for certain kinds of relationships. Here, we have, you'll remember, we had this log parameter where, so let me just go back to it. We had this thing. We had the log of the lambdas. These are linear. It's linear in logs, but they're linear. What the generalized linear model does is allow us essentially a simple extension of these kinds of approaches to any linear function. We called this log the link function, but we can do this with really any function we wish. The main idea is that we can put in a linear function in the parameters into any general function, which in this case is log, and then we can estimate using just classes of link functions. So in this case, the thing we're doing is we're using a log link, so the log of that lambda. And stats models actually just has a built-in function for this. So I'm gonna run this model. This is just using the original data. I'm just reshaping it so that it'll fit into our structure. So this is attack team and defense team. I have the goals for the attacking team and the goals for the home team. And then all I'm going to do is estimate using an indicator variable for the home, and then controlling for the attack and the defense. And when I run this, I end up with exactly the same parameter values as in the model we built from hand by scratch. Built from scratch by hand. So you can go through and just double check. I think it's a little hard to do this in the in slides like this, but if you go through and you check the estimated values, this is estimating the attack parameter, or alpha, for this team. This is the estimated coefficient, so they have a bad attack score. And then we also get standard errors, which is incredibly nice. When we're performing these estimation techniques, what we've just done with our hand-rolled version is estimate just the coefficients themselves. So these are just the estimates. But the question that remains is whether these estimates are different from some hypothesis, right? Like, are these actually meaningfully different? Well, that question obviously is left unresolved. All we've done is estimate the values themselves. So just to say this, you can go through and check the numbers here, but this is one estimate, and then the generalized linear model is another estimate. Okay, and they should at least correspond somewhat closely. Okay, any questions? Any questions? Any questions? Yeah, Wei.
What is the pseudo
Pseudo R squared. So let's see. This is here. So this is I can't give you great intuition for what this is doing. It's like a generalized linear model version of the standard R squared. But I don't have a lot of intuition for how it differs from the OLS R squared. But yeah, it's a good question. I can look it up and get back to you. Any others? So, the GLM gives us standard errors, which allow us to check for confidence intervals. So this allows us to make claims about, the consistency of our estimate with any hypothesis we wish. This is really nice. This is what we call inference. Often we, every time we observe some observation, it's simply one draw from an underlying probability distribution. We know through theory sampling distributions. So what we want is some way of constructing the sampling distribution, centering that on our hypothesis, and then making claims about the consistency of our hypothesis and our estimate. So if you're testing, like, is this actually different from zero? Well, we need a standard error to make that happen. So what we're about to do is actually construct standard errors. In OLS, this is pretty simple. Like, in the scheme of things, right? It's the sample standard deviation divided by the square root of the sample size. With maximum likelihood, it becomes a little more complicated. I hope we can breeze through this. I want to show you a couple of techniques and a couple of theory elements. I don't feel a strong need to dwell on this. We're going to use these ideas throughout the rest of the semester, but hopefully we can get through most of this today. So if it feels too fast, you let me know. But the broad outline is we've gotten to this place. We've developed the computational tools to be able to run maximum likelihood on likelihood functions that we can't evaluate analytically. Like, we've developed all this machinery to be able to build more sophisticated models than we can do by hand. And then we built maximum likelihood. We estimated a model for the parameter estimates directly. What we're about to do is figure out how to make standard error claims. So how precise are our estimates. This is what we call inference. So the point estimates are just a half of the story. I think we've done most of the work already, but we also need to think about the precision of our estimates. By half of the work, I don't mean half of the conceptual work. I think the point estimates go hand in hand with the standard errors. I think you can't separate the two ideas. One without the other is just not that useful. Yeah, this is me trying to convey to you that standard errors are at least as important as our point estimates. So we have to understand the sampling distribution of maximum likelihood. So we build these point estimates, and then we think about how close, like essentially the variability in the point estimates themselves. Okay. Specifically, we're going to use the variance covariance matrix. And we can do this. We're going to start first theoretically. So we're going to outline the asymptotic properties of these estimates. I'm going to give you the Fisher information matrix, and then we're going to use the Hessian, which we slogged through a couple of classes ago. And then we're gonna apply this. And if we have time, we'll talk about the delta method, but I might leave that for extra. All right. So maximum likelihood. So if the likelihood function is smooth, and we've correctly specified our model and identified the parameters, we've defined the parameter space correctly. We have three asymptotic properties for MLE. One is consistency, so the point estimates go to the truth when our sample size grows. With enough data, we're getting super, super close. The distribution of the sampling distribution approaches normal. This is, you all are familiar with the central limit theorem set of ideas. That's what's happening here. We get this distribution. So it approaches normal in distribution. What's nice about this is we don't actually need to know the underlying distribution of the data. We know the distribution of the sampling distribution by this result, essentially the central limit theorem. And then efficiency, that maximum likelihood actually does the best possible theoretically. Like, there isn't a theoretically better approach for efficiency. The variance is as good as it gets with MLE. And remember, this is all under the assumption that we have a smooth likelihood function, the model is specified correctly, and it's been identified. Okay, so these are all with large sample size results. But we can also use these tools for small sample sizes. We just have to sort of think carefully about the details. Okay, so this is the first big concept, which is we're going to take this is what we call the score of the likelihood. This is for any parameter. We take the first derivative of the log likelihood function. This is what we call the score. It's a vector of first derivatives. This is just written out in vector notation, but you can think of each element as just being the first derivative of the log likelihood with respect to the parameter value theta. This is what we call the score. It's this thing. This matters because at the true parameter, the score is 0. So we get that sort of like, you can think of those pictures we drew of the likelihood function and where it's maximized. The score is basically just the gradient of the log likelihood function. So there's nothing like truly different here. The first order conditions for the maximum likelihood are just setting the score equal to 0. That's all this is. So we've seen this before. We've dealt with it. Are there any questions about this? Okay. So the maximum, so we set this equal to 0. But this, it varies from sample to sample. So like for our specific sample, it's not going to be exactly equal to the true parameter, our maximal likelihood. Because each time we resample, just simply due to sampling variation, our data changes, which changes our estimated parameter values. But on average, this gets us to the truth by the central limit theorem. Law of large numbers too. Okay, so then the second idea is what we call the Fisher information matrix. Has anyone seen this before? Okay, so this, do y'all love the way this looks? There's a lot going on here, but it's fundamentally not a particularly complicated idea. So let me just talk you through it. There are two generally equivalent formulations, and I think they have to be asymptotic for them to be equivalent. So the first one, actually, let me rescind that. I think these are mathematically identical. So the first one, this is how we define the Fisher information matrix. It's just the big I of the true parameter, which is just the expectation of the squared scores. So remember what the scores are? It's just the first. It's like the first derivative of the log likelihood function. All we're doing is essentially getting the variance of the score. So variance of the score. This is mathematically identical to the second derivative, the expectation of this. So this is the variance of the score. This is the just the expectation of the second derivative, but negative. We're going to focus on the first one. I think the intuition is easier. So the information matrix is essentially just like how flat the first derivative is around the truth. So like almost like the curvature of the log likelihood function on average. The reason we're using averages, as I understand it, is because we want to understand not just our particular sample, but how it is on average, essentially. So the core idea, it turns out, is that the variance of our samples is approximately equal to the average Fisher information matrix inverted. There's more theory here for how Fisher did this. Fisher was like one of the big pillars of statistics in the 1900s. There's lots of details for how this came about, but and in general, I don't like just giving definitions without motivating it too much. But essentially, this is like the Fisher information matrix gives us something related to the curvature of the log likelihood function. And the variance is related to the sort of the curvature of the log likelihood function, the parameter values. So the smaller this thing is, the more precise the estimates. So you can think of like, if our maximum likelihood function is, if our likelihood function is very, very sharp, so if it's very steep around a particular parameter value, we're going to be very certain that that parameter value is close to the truth. If the gradient is really tight, then the parameter value is not going to vary much between samples. And so our variance will be small. That's the intuition for what this is doing. I could draw you pictures, but three-dimensional pictures are kind of challenging. But just think of like, we have like a manifold over some dimensional space, and we're just thinking about the steepness of that shape. The steeper it is, the tighter it is, the smaller is the curvature, and the smaller the variance, or the tighter the curvature, and then the smaller the variance. Any questions here? So all you really need is the intuition for what this is doing, and then we're going to go about computing it. Another big idea is the Cramer-Rao inequality. I learned this from someone with a French accent, so I don't know how to pronounce this properly in English. Cramer? Kramer?
I think that's the English pronunciation.
It's at least, yeah, a character on a TV show.
I guess Jim Cramer, the finance guy.
Oh, true, yeah. Isn't there like it's the inverse Kramer rule? It's like whatever he says, you do the opposite.
Yeah.
I don't know anything about finance, except that one, fake Reddit rule. What this inequality tells us is that the variance can't be smaller than the average inverse Fisher information. And it turns out that the variance under MLE is exactly equal to this. So this is the efficiency result. MLE is as efficient as it gets. You can't get smaller variances than what you do in MLE. Okay. No better than ML. Just to say MLE. This is not a machine learning class. I guess Andy kind of taught you some ML stuff. And this is all ML. Okay, so this is just some theory. We've talked about this. I think we did exactly this in the previous slide. But the question at hand is what the score of the log likelihood is, or the score is, which is the first derivative of the log likelihood. I came into this class thinking I would have you try to do this, but I think for the sake of time, I'm just going to show you these results. If you want to go back and try to replicate what I'm doing with the derivatives in the slides, that would be a good thing to do. But I think you all are probably pretty familiar with doing derivatives. Okay, so we get the score simply by taking the first derivative of the log likelihood with respect to the parameters of the model. In this case, the parameter is just lambda. We've done this before. This was our first order condition in the last slide, last notebook, when we were doing Poisson at the very beginning. But this is the score. So we could set it equal to 0 to solve for lambda. But this is how we define the score. So the thing we want is to find the Fisher information, which is going to give us the variance. The first way of finding the Fisher information is with the score. So we talked about this formulation before. So Fisher information was equal to the expected value of the score squared, which this is the same idea as like a second moment or the variance, right? Whenever we have something inside the expectation operator squared, we do this to calculate the variance or the second moment. So this is just the essentially the equivalent of that, sort of the curvature. So we've talked about the information matrix as the curvature, which is what this is doing. So to do this, you have to find each observation, square them, and square the whole thing, and then take the expectation. And you can do this. But we're not going to. This is the hard way. You can just, what we want is this thing. So we have to sub in S lambda and then expand it and then take the expectation. We would need to know the expectation of Ki, which is lambda, and then we need to know the expectation of Ki squared, which would be lambda as well. So we can just plug all this in and solve. But there's a much easier way. And that's with the Hessian. So we've talked about the Hessian, which is the second derivative of the log likelihood with respect to each of the parameters, which, because we're taking the second derivative with respect to each of the parameters, if this were a higher dimensional space with more than one parameter, we'd have a matrix. But here we just have one parameter, so it's just the second derivative. And then we just take the expectation of this thing. The thing is here, with the Poisson, we can just take the second derivative directly. That's this thing, so it's the first derivative of the sum, which then just gives us this. So it turns out, like, most of the time, this is just going to be a much faster approach. We take this thing and we plug it into the expectation operator, and it comes out to be this. And then we just simplify. And this is identical to the way we did before using the score. So these are the same answer, same math, just like slightly different approaches. Okay, 2 approaches, same result. That's always very comforting. The CR inequality tells us, I'm not going to try to pronounce that, it tells us this inequality, and MLE tells us that the variance will be equal here. So if we found the Fisher information, we can plug that in where we have, so this is the Fisher information, we invert it. And I think this is a typo. If this is a typo, I'll correct this and let you know. But let's keep rolling with this. I just need to double check that the math here is right. Let's go under the assumption that this is right, and then if it's not, I'll let you know. So the MLE estimator, as we've already established for lambda, is just the average of k. So the average in this specific example, Poisson distribution with k observations, n observations, is just k bar. We know it hits this lower bound, so the CR lower bound, and and we get a standard error of the square root of lambda over n. So the nice thing about this is we have a very simple estimate of lambda, and this is as good as it gets for standard errors. So nothing beats this. So for example, if we have 400 observations with a Poisson distribution of 2, so each one is IID drawn from Poisson of 2, lambda is 2, so we can take the standard error using this. So the standard error plus the estimate gives us all we need to know to make inference, right? We have the standard error. We know it's approximately normal, so we can use like a t-distribution or a normal distribution. And then we know the point estimate directly. So then that allows us to do all of our standard like hypothesis testing on our estimates. And remember, this is the standard error on lambda. This is not the distribution of k's. This is the sampling distribution of the parameters, which I think, having taught these ideas for a very long time, is one of the most misunderstood parts of what we're doing. This is the standard error is about the model parameters. So the distribution of lambdas, not the distribution of k's. All right. We can do this more generally. So we can talk about the variance covariance matrix, which is this thing. So we just talked about for a very specific example, but we can calculate the variance covariance matrix for larger types of things. The problem, though, is that in general we don't observe sigmas, which is like, isn't that the whole point of doing these estimations? So what do we do? Well, we're going to plug in our best guess, which is sigma hat. The reason this works, replacing the true sigma with the guess, is because MLE is consistent in the limit. So as the sample size goes up, we get closer and closer to the truth. In small samples, we have to make a bit of a correction. Think like t-distribution versus normal distribution. But in large enough samples, the t and the normal distribution are identical, so or nearly identical. So we don't usually bother with that in large samples. Okay, so small samples, it's an approximation. In large samples, those things are very, very close. Okay, so, and then everything else basically just follows. We'll construct standard errors just like we did in OLS. It's just, here we're using the variance covariance matrix to get the standard errors. Okay, any questions here? Hopefully the high level ideas are pretty clear. What we've done is said, we've gone through this whole procedure of setting up the likelihood function to then give us more structured ways of building statistical models. We've then just simply used our nonlinear methods, our numerical methods, to use a gradient approach to find the point estimates. But then we can then just use the score or the Hessian to get us the Fisher information, which then tells us the standard errors of our point estimates. And the reason we need this is because we want to make claims about like how precise our estimates are. Are they different from 0? Are they different from other values? And that's all making claims about the parameter values, not making claims about the data itself. So these are the two methods we've just walked through. Both are the same. I think the score method is harder mathematically, but cheaper computationally. and then the opposite is true. So we talked about using the Hessian to compute the Fisher information, but it's easier mathematically, but harder computationally, because we have to do those two derivatives. We have to approximate 2 levels deep. Okay, any questions here? Nice. So let's just. I think we can get through this. So let's do a bit of an example here. We've talked about the Poisson case. Let's just run a few things. So here I've just sampled 400 observations and found that the sample lambda hat, so our theoretical lambda estimate, is very close to the truth. And then we can just calculate the score. So the score for observation kj is just this thing. So this is kj over lambda minus 1. It's just the derivative of the log likelihood for that observation directly. So if we want to get this, just simply looking at a single Poisson observation, and we to calculate the score, we would first construct the Fisher information, which is the score squared. This is just the analytical score. So we took the first derivative. We know how to do that analytically. I'm just encoding it in a function. And then I'm plugging into the score the observed value k. Or I should say all of the observed values k. And then what I'm doing here is so I'm just running this for all of the observations, and then plotting out the average squared score, which is the expectation of the squared scores. And this gives us the Fisher information, the sigma hat. And when I run this, I get this number, which is really, really close to 2. Any questions here? Which is exactly what we'd want. So to get the standard error, the asymptotic result says that the difference between the estimate and the truth times the square root of n has this variance. You can also think of this as, like you can multiply both sides by square root of n. So lambda hat itself has, or divide both sides by the square root of n. But because the variance squares that n, you end up with the sigma matrix over n. So it's sigma over n. And then the standard error is this thing. So this is just the square root of our estimate of that. Okay, lots of econometric theory here. And this is the asymptotic variance that we've calculated using one of the two methods. So let's just estimate this. Here we have so we calculated sigma hat before. This was the inverse of I hat. So this is sigma hat. Just using the inverse of the information matrix, and then all we're doing here is just computing the standard error, which is that sigma hat divided by n, and then we're just taking the square root of it, which is the same procedure as OLS. So this tells us the estimate for lambda. It also tells us the spread of the sampling distribution of lambda, the standard error. So remember, the standard error is just the variance of the sampling distribution of the parameter that we're trying to estimate. That's how we define the standard error. It's not the standard deviation of the data, right? This is a claim about this. If we take another sample, how spread out is the parameter estimate that we would construct from that new sample. So each time we take a new sample, we run this model, we get a different parameter estimate. How spread out are those different parameter estimates over like 1,000 samples that we build statistical models over? Okay, so nice. This is really tight. Which is really good. This is the theoretical best we can do. So that's pretty amazing that we can't do any better than this. So nice. The true standard error is this thing. So this is just, I know exactly the sample size. I know the true standard deviation, the true sigma. So I can just plug that in instead of using the sample. And this is pretty close. So our estimate was 0.069, and the truth was just over 7, 0.07. So we're very close to the truth. Okay, so I've included this little bit here. I want to show you a picture of the sampling distribution. The true sampling distribution, like what I'm doing with this is just repeatedly sampling different parameter values from the underlying true distribution. So it's as if I'm just repeatedly drawing over and over, I'm estimating, and then I'm plotting a distribution of the lambda parameter values. I'm taking the difference between the truth and the estimate, just so it's centered on 0. But this is, so the truth, we get really close to the truth most of the time. And then you can see the spread. Was that a question? No. Just eager for questions. In college, someone sat in the back row, a friend of mine, he'd like rest his hand kind of like this above his head. And he'd sometimes like do this by accident, and he'd get called on all the time. So this is the true distribution of the lambdas. Like, this is showing essentially what would happen if I were to draw new data sets over and over again and plot like a histogram of the density of those lambdas on the horizontal axis. And what you can see, the truth is in yellow, but the thing we estimated is in blue. So they're very close. Using this estimation procedure, we get very, very close to the truth. And not just the true parameter value, but the true distribution. I would say these are nearly identical. We overestimate, we get like slightly too confident. You can see the top of the estimated one is just slightly above the truth. And you can maybe think intuitively about why this is true. The MLE slightly is too confident with small samples. You remember that because, I mean, in OLS, we had 1 over n minus 1. And then for the standard deviation, in MLE, it's 1 over n. So we just get slightly too confident. Okay, any questions about this? Can I just say this is amazing? Like, we're not just point estimating, we're not just fitting a model, but we're getting a distribution of the model estimates. If, like, in the hypothetical world where we were to rerun this a bunch of times, we can't do that. We cannot rerun our sample. I mean, I guess you could. But the point is, we don't need to, because we can just approximate this distribution using information that's embedded in the single sample that we observed. And then all this amazing, beautiful theory about how we construct the standard errors from our sample spread. every time I see this stuff, that part amazes me. That we can get the distribution just directly from the sample. The distribution of the what would happen if we were to rerun this over and over and over again. Are you not amused? No. Are you not entertained? That's the quote. Okay. I guess the answer is no. We are at the end of class, so there's that. Okay, so we could do all this again with the Hessian. I just want to put this on screen. This is maybe even a little bit better. The estimates are slightly different. This is not identical to the score calculation, but they will be the same in expectation. It's just the approximation methods we use are slightly different, whether you're using the Hessian or the score method. You all might be having nightmares over these things after question 1 on the last checkpoint. But all we need to do is perform approximations of this stuff. We use the centered approximation because it's better. And then all I'm gonna set this up using these analytical solutions. And then this was just a Monte Carlo to show you that everything we just did was right. This is the theory for the standard error. This is the truth. And then this is just like a gazillion different observations. I'm running each model, showing the distribution of the lambda hats, and it fits our model really nicely. We can do this with multiple parameters. I'm going to spend a second thinking about whether we want to start next class with this or we start with the GLM. This is just me walking through the like a more complicated setup, which then kicks us off into the estimating the standard errors of the soccer example we just set up in the previous notebook. Take a look at this. There's a chance we might not do this in class. I'll spend a second thinking about whether we do it or move on to GLM. Checkpoint tomorrow, 1 to 3. If you can't be there or don't want to be there, send me an email and I'll give you the code for all the materials and an extension through Monday. Don't lose sleep over these things, but do put in the work. Have a nice weekend. I guess I'll see you tomorrow. Get some sleep. You will get jobs.
Lifeguards.
Yeah. Everyone will be a lifeguard.